Okay, so that's ionic compounds. The ionic compounds, you always just show the metal empty with a charge, and nonmetals are full with those dots. That would be typical for an ionic compound. What about covalent compounds? They still hold on to their electrons, and they still want to get 8 because those are more likely to be more than half filled with electrons, and so they want to get 8 from each one. So we're going to have to go through a little separate process in this sharing. It's like going out for pizza with friends, and let's say you all have, somebody's got $1, somebody's got $20, somebody's got $5. You all want to throw it in and just say, whatever. We're going to all work and be satisfied that we have this. So they throw their outer shell electrons into a bucket or into the pot, and then they say, well, whatever, we'll get pizza and we'll make sure everybody's got what they need. And that's what's going to happen when we're going to do these electron dot structures for covalent compounds. Now, we're still going to use dots, but we're going to use a shortcut system where 2 dots becomes a line. So I might call the previous one electron dot structures, and these I'm going to call Lewis line structures, we'll try some of these, okay? So when we're talking about covalent compounds, things from the nonmetal side react with other things from the nonmetal side, the electrons in covalent compounds aren't as easy to track. You can't tell, where they're coming from. So you're just going to throw them into a bucket and a pile, as they were in the ionic compound. So we're not going to use those. We're going to use, instead of 2 dots, we're going to just call 2 dots a line. So instead of saying, hey, here's these 2 dots from some element, instead we're going to draw it as a line, and that's the same thing as 2 dots, all right? There's some magic to it, and I'll show you in a bit what that reason is. So in these Lewis electron dot structures, this method differs only in that the line is there instead of 2 dots. Otherwise, it's the same kind of process. So when we draw these Lewis structures, let's take an element like CH4. You're still going to figure out how many electrons are in the outer shell for each of those. So the carbon, for instance, is in the 4th column. So it's got 4 electrons. Okay. Each hydrogen has 1 electron. It's in its own column having 1 electron, but there's 4 of them. So you take 4 times 1, giving a total of 4 electrons. So I take 4 times the 1 electrons, and we add those up. 4 plus 4 is 8 total electrons. You find out how many total electrons the whole group has, and you put them into a single bucket, single pot. Okay? Now, what you're going to do is you're going to lay out the skeleton structure. By that, I just mean lay out the atoms the way they would be normally arranged. Usually, there's a center atom, one atom that's in the middle. The closer it is to the center of the periodic table, the more likely it is going to be the center. If there's only one atom that's one of that atom, that's usually the center atom. So if it's like CCl4, okay, C is closer to the middle of the periodic table, but there's only 1 carbon, so that's the middle atom. In this case, there's 1 C and 4 H's. So I'm going to lay that out over here. It's already done for us in the notes, but I'm going to lay it out here, and I'm going to put the 4 H's around it. Okay? That's the skeleton structure. And I know I've got 8 electrons to put around every atom, and every atom wants to usually have a full set of electrons. So let's start with putting electrons between every atom. So instead of writing them like we did this last time where we had dots, I'm going to write instead a line. So that line shows 2 electrons, 2 electrons, 2 electrons, 2 electrons. I've got all 8 of my electrons out. Now, the way that we put them in here, let's move this up a little bit, is that I want to join all the atoms with a pair of electrons or a single line. Okay? And I want to see if I can get every atom to have a full outer shell, or an outer shell that has 8 electrons for most things, but hydrogen's an exception. Remember, hydrogen only has a 1s, and so the most it can have is 2. When it has 2 electrons, it's happy. Right now it starts off as a 1s1. But this carbon has some electrons, right, and it'll share that, and so we're going to see if we can't make it have 2. We don't care where they came from. We said, does this hydrogen have 2? Yes. Does that hydrogen have 2? You can count the electrons that are being shared as both the atoms. So this atom's saying, I like those 2 and I'm happy. But this carbon can say, gosh, I like these 8 electrons and I have a full outer shell, so I'm happy. And the compound wants to have 8 in its outer shell except for hydrogen, which only wants 2. Okay? Forget where the atoms came from. You put those lines down and you draw them out so that every atom gets as many as they can. In other words, they shoot for 8. So let's try a little bit more challenging one. Okay. Number 4, if every atom has got a connecting pair of electrons, the rest of the atoms you have to find out where there's a home for them. So that was an example that was already done once I finished that. So let's take a look at another one where it's carbon and 2 oxygens. Okay, I'm going to pull this up a little bit. I'm going to do them again, even though they're in the notes. But if I'm going to start off with 2 carbons, okay, this is the way I would do it. Okay, a carbon has 4 valence electrons. Usually I put the word VE for valence electrons. I've got 4 for that carbon. Each oxygen has 6 because of where it is in the periodic table. It's the 6th column over, and there's 2 of them, so that's 12 valence electrons. So totally I have 16 valence electrons. Okay, that's what the notes are showing. Now, I'm going to write down the skeleton structure. I have 1 carbon and 2 oxygens, so the carbon must be in the middle. Oxygens must be somewhere around it. I'm going to put an electron pair between each one. I'm going to put 1 line between each one just to get them started bonding. That's where you start putting your electrons, okay? So I've got 2, 4 that are total. I've taken 4 out of the total 16. I've got 12 more electrons to put. I'm going to try putting them around the rest of the atoms to make every atom get 8. So I've got 4 out, that means 12 left. So 12 I have left. There's 10, 8, 6, 4, 2, 0. In other words, 2, 4, 6, 8, 10, 12, 14, 16 electrons I've divvied out. Now, I've made the oxygens happy because they've got 2, 4, 6, 8. And this oxygen's happy too because it's got 8. But the carbon in the middle is not. I've run out of electrons. That's all I have to use, 16. But the carbon is not happy. So I have a trick that I want you to try. And the trick is try a double bond. In other words, take one of these pairs of electrons. There we go. And instead of making it just out here on one atom, stick a second bond in between and see if that doesn't help. I still have 8 around this atom. I have now 6 around the carbon and 8 around this oxygen, and I still have my 16. 2, 4, 6, 8, 10, 12, 14, 16 electrons. But I haven't satisfied both, so I've got to do that trick twice. So I'm going to erase those electrons there. And I'm going to put a second double bond in here. And that way I get 8 around the carbons, 8 around the oxygens, and I've used all 16 of my electrons. And that makes it happy. So there is a trick. If after you've tried to divvy out the electrons to get everybody happy, after putting 2 electrons, a line between every set of atoms, then you're going to see if you can't get a trick of double bonding and get every atom then to have what it needs. Okay, try those out on the worksheet assignment, and there's some answers also posted for you.